Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
You know the feeling? You're running a bioprocess, the fermentation broth looks beautiful, the titer is high. I mean, everything is going just perfectly to plan. You send it to filtration, and then, well, the inevitable happens.
A slug.
The flow slows down, the pressure spikes, the pumps are, practically screaming. You are officially clogged.
It really is the central conflict of bioprocessing. It's this constant battle against the gunk. But what's so interesting is that for a long, long time, the industry sort of treated this like bad weather.
Right. Oh, it's just clogging. That's what filters do.
Exactly. Like it's some act of God.
But the stack of research we're diving into today, and it covers everything from Hermia's fouling equations to hybrid digital twins, it says otherwise. This isn't random. It's physics.
And if it's physics, we can model it, we can clean it, and ideally, we can predict it.
That's the mission then. Moving from just guessing why a filter is blocked to, I guess, mathematically proving it.
That's it. We're looking at technical papers on fouling, we're looking at industrial best practices for clean-in-place systems, and some really fascinating data on how to build a digital twin that knows your filter is going to fail before you do.
Okay, so let's start with the detective work. We have these papers, they keep referencing Hermia's equations. Now, when I see a set of equations from the 1980s, I brace myself for a dry math lecture.
I get that.
But this felt different. It felt more like a criminal profile, a way to identify the suspect.
That is a great way to put it. Hermia isn't just a label, it's a mathematical fingerprint. It maps the decline in your flux, your flow rate, to specific archetypes of fouling.
And it all comes down to one number.
It all comes down to the exponent n in the characteristic equation. Depending on whether that number is 2 or 1.5 or 1 or even 0, the math tells you exactly how the crime was committed.
So let's run through the lineup then. What are the main scenarios Hermia gives us?
So the first one is complete pore blocking. Imagine you have a sieve and you drop marbles onto it. The marbles are basically the same size as the holes. They land, they seal the hole. Game over for that pore.
The door is just slammed shut.
Effectively.
Yeah.
Then you have what's called standard pore blocking. This one's a bit more insidious. The particles are smaller than the pore, so they go into the channel, but they stick to the walls.
Oh, like cholesterol in an artery.
Precisely. The channel just gets narrower and narrower over time. Then there's intermediate pore blocking, which is, a mix of the two.
Right.
And finally, the most common one you'll see in these high-density broths, cake filtration.
Which is exactly what it sounds like. You're just building a layer of lasagna on top of the membrane.
A dense, compressible layer of lasagna. And here's the kicker. In true cake filtration, the membrane itself isn't even doing the filtering anymore. The cake is filtering the liquid.
Now, here's where I got a bit stuck reading the sources. Hermia, he developed these models for dead-end filtration.
Right, like a coffee filter.
Yeah, you pour water in, gravity pushes it down. But in bioprocessing, we use TFF, tangential flow filtration. Everything is swooshing sideways across the filter. Yeah. Doesn't that just break the math?
It definitely complicates it. I mean, in TFF, you have this thing called back transport. The crossflow is actively sweeping particles away from the surface. Hermia never had to account for that.
So for a while, people just thought, well, we can't use these models.
They did, but the sources argue that you just can't be lazy about it. You can't just take the equation, slap it over a 3-hour run, and expect one single answer.
Because the broth itself is changing. The soup you have at minute 10 isn't the same soup you have at hour 3.
Exactly. You have to use regime identification. You segment the data. The first few minutes, that might be classic pore blocking little fines plugging up the holes.
But an hour later?
An hour later, once that surface is covered, you've transitioned into cake filtration. If you try to average those two very different physical events into one number, you just get garbage data.
So the workflow is normalize your signals first, get rid of the temperature and viscosity changes, and then look at the slope in these different time windows.
That's it. You strip out the trivial drift, and then you fit the candidate models to the segments. It actually tells you the story of the run.
But there is a catch. The sources talk about non-identifiability.
This is the great frustration of the field. Sometimes, two completely different problems, like a certain type of pore blocking and a certain type of cake formation, can produce a graph that looks almost identical.
So you're looking at the data, and it could be suspect A or it could be suspect B, and the math just you can't tell them apart.
Not if you just sit there and watch, no. If you don't perturb the system, if you don't change the pressure of the flow, you might never know for sure what's killing your process.
Which brings us to the next logical step. If we can't always identify the mess once it's made, we should probably try to prevent it. This brings up the idea of critical flux.
This is, I would argue, the most important operational parameter in all of filtration. The critical flux is the tipping point.
The line in the sand.
It is. Below this flux, the drag forces pulling particles to the membrane are balanced by the lift forces from the crossflow sweeping them away. You're in a safe, sustainable zone.
And if you go above it?
Above it, the balance breaks, the drag wins, cake starts to build up, and fouling begins to spiral out of control.
That feels like a trap, though. Because as an operator, I want to push for speed, for high throughput. But you're saying there's a specific velocity where the physics just turns on you.
It is a trap. And the only way to find out where that trap is set is to run a flux stepping experiment.
Okay, walk us through that. How do we find this number?
It's essentially a stress test for your process. You start the machine at a very low, safe flux. You hold it there for, say, 10 or 20 minutes.
Right.
Then you step it up, add maybe 5 or 10 LMH, and you hold it again. And you keep doing this while watching the transmembrane pressure, or TMP.
You're waiting for the pressure to twitch.
You're waiting for instability. In that safe zone, the pressure will be stable for each step. But the moment you take a step up and that pressure starts to rise, just to maintain the flow,
You've hit it.
you've hit the wall. That is your critical flux.
And the sources have this really sobering case study on glycerol fermentation broths. This wasn't just theory. They had data showing what happens when you get greedy.
A crucial study. They looked at crossflow microfiltration of this glycerol broth and found that when they increased the driving force, when they pushed the TMP higher to try and force more liquid through, they didn't just foul the membrane faster.
They actually changed the kind of fouling that was happening.
They massively increased the percentage of irreversible resistance.
And that is the absolute nightmare scenario. You think, I'll just run it hard and clean it aggressively later, but the data says, no, if you run it too hard, you might not be able to clean it at all.
Exactly. You are literally driving the particles so deep into the membrane structure that they lodge there permanently. You've done permanent damage.
You've hurt the membrane.
And no amount of cleaning is going to bring that permeability back.
Well, speaking of bringing things back, let's say we did hurt the membrane. Or even if we didn't, the run is over. We have to clean it. The sources go into a lot of detail on CIP clean in place. And my biggest takeaway here is that most of us are probably cleaning our filters wrong.
It is highly likely. Cleaning is chemistry, it's physics, but it's often treated like, doing the dishes.
You just scrub till it looks clean.
Right. But in bioprocessing, you have to understand the taxonomy of dirt.
I love that phrase. But it's practical, isn't it? If you don't know if you're fighting protein gunk or mineral scale, you're just guessing with your chemicals.
You're guessing. You have 3 main categories: organic deposits, so proteins, lipids, cell debris. You have inorganic scale minerals. And then the worst one, adsorbed macromolecules way down inside the pores.
So you need a strategy. The sources lay out the 4 energies of cleaning.
These are your levers. You have kinetic energy, which is your flow rate, chemical energy, your regen concentration, thermal energy is temperature, and then, of course, time. And you have to balance them.
And there's a specific sequence to it, a proper order of operations.
There is a defensible UFCIP sequence. It almost always starts with a simple water flush.
Which seems so obvious, but I bet people skip it or they rush through it.
They do, and it's a huge mistake. You have to remove that loose bulk material, the easy dirt, before you bring in the chemicals. If you don't, you're just wasting expensive, caustic fighting sludge.
So water flush first, then what? Typically caustic.
Caustic, yes. An alkaline wash to eat the organics and the proteins. Then an acid wash, which does 2 things. It neutralizes the caustic and it dissolves any minerals or scale. Then a final rinse with water until your conductivity is back to baseline.
Now, there's one rule in the sources about cleaning that really stopped me in my tracks. It feels completely backwards. High flow, low pressure.
It is the most common and most damaging mistake in the industry.
Because my logic says, if I want to clean a clogged pipe, I blast it with high pressure. Why can't I just blast the membrane?
Because a membrane isn't a pipe, it's more like a sponge. If you hit it with high transmembrane pressure during cleaning, you aren't washing the dirt off the surface. You're driving it into the structure.
You're compacting the cake.
You're turning a loose layer of dirt into a solid brick. You want high flow, that's high velocity sweeping across the surface to scour it clean, but you want the pressure pushing through the membrane to be as close to zero as possible.
High shear, low permeation. That's a stick-it-on-the-wall kind of rule.
And the other rule is don't wait. Deposits age. The longer a protein sits on that surface, the more it changes shape and locks in. A filter that's dirty on Friday might be unrecoverable by Monday.
Okay, so we've covered the physics of the clog with Hermia, how to avoid the tipping point with critical flux, and how to clean up the mess with this high-flow, low-pressure idea. But the sources all point to a future where we don't have to be so reactive. They talk about digital twins.
This is absolutely where the field is heading. But we need to be clear, this isn't just some 3D CAD model of your filter housing sitting on a screen.
Right, it's a hybrid twin. What does that actually mean in this context?
It means it fuses the hard physics, those resistance and series equations we talked about, with an AI layer on top.
Why do you need both? I mean, if AI is so smart, why not just let it learn the whole system from the data?
Because purely data-driven AI, it needs massive amounts of data to learn, and bioprocess runs are really expensive. You can't afford to run 1,000 failures just to train a neural net. The physics provides the guardrails.
The common sense.
The common sense of the system. It already knows that flux should go down as resistance goes up. The AI doesn't have to learn that from scratch.
So the physics is the map, and the AI is, what, the live traffic?
That is a perfect analogy. The mechanistic core is the map. It knows the roads, the speed limits. That's the physics.
Right.
But the AI layer is the live traffic update. It knows that right now, today, there's a cell lysis releasing DNA into the broth that the static map couldn't have predicted.
Got it. So the hybrid twin combines the map and the live traffic to give you an accurate arrival time.
Exactly. It often uses a tool like a common filter to do this.
Which is basically a sophisticated way of separating the signal from the noise, right?
Right. And it estimates the hidden states. You see, the pressure gauge on the wall, it just gives you one big number, total resistance. It doesn't tell you why. The common filter inside the twin can look at the noisy data and estimate, okay, 60% of this pressure is just reversible cake, but 40%, that's irreversible pore blocking.
And that is the holy grail. Because you're not just seeing system is clogged, you're seeing system is dying.
And that allows for predictive control. The output isn't just a graph, it's a decision tool. It gives you time to limit. It says, if you keep running like this, you will hit your maximum pressure in exactly 40 minutes.
Or recoverability risk.
Yes. If you push for another hour, the irreversible fouling will be so high that your CIP protocol will fail. It lets the operator stop the run before they destroy the asset.
It changes the entire game from run until failure to run until the optimal stopping point.
It does. Now, the sources are clear this is still hard. The feed evolution problem, the fact that the biology keeps changing mid-run, means the AI has to be very, very adaptive.
So let's wrap this up. We've gone from the detective work of Hermia's equations, figuring out if it's a seal or a layer, to the trap of critical flux. We've learned that cleaning requires that counterintuitive, low-pressure approach.
And we've seen that the future is these hybrid twins that can tell the difference between a filter that's just dirty and one that's truly ruined.
It really highlights that filtration isn't some passive step where you just cross your fingers and hope for the best.
Absolutely not. And if I can leave you with one final thought, it goes right back to that idea of a carifiability we talked about at the very beginning.
The idea that different problems can look the same on a graph.
Exactly. If pore blocking and cake filtration can produce the exact same pressure curve, we have a blind spot. And this raises a really provocative question for the future of how we operate these systems. Can we ever truly know what's happening inside the filter without disturbing it?
What do you mean?
Well, perhaps the future of filtration isn't just passively observing steady states. Maybe we need to intentionally disrupt the system, do little flux steps, cycle the flow, perturb it in small ways, just to see how the system reacts. We might have to shake the box a little to find out what's actually inside.
You have to poke the bear to see if it's just sleeping or if it's waiting to bite.
Exactly. Passive observation might not be enough anymore.
That is a fascinating thought to end on. Filtration is an active interrogation of the process.
Yeah.
Thanks for taking this deep dive with us.
My pleasure.
And thank you for listening. Hopefully, the next time your pressure gauge starts to spike, you won't just see a problem. You'll see a puzzle waiting to be solved.
Okay.
We'll see you next time.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.